All right, so in this section, we're going to talk about an application of Boolean algebra when we talk about gates and circuits. Right? So we think of computers to be just very logical. Right? So what we're going to do is we're going to look at this idea of a circuit, right, and how to wire these circuits using the propositions that we already know and that we've calculated with Boolean algebra, right? So we're going to talk about something called a logic gate, which is a tiny electronic component that takes on one or two wires. These are called inputs, right? And produces one wire as an output, right? That computes one Boolean operation, right? Now, when we talk about a wire, what I'm referring to is if we take a look at this, right, not necessarily what we think of as like the wire on like our headphones or our charger, right? So we think of a wire that looks something like this, more like a trace and like a circuit board. So it'll transmit an electronic signal, and from there, right, that electronic signal will something whether the signal will represent whether it's on or off, right, or true or false, I should say. Right, and feed into some kind of logic gates, right, where it takes in that input and then sends out an output, right? So our logic gates, we have three of them, three fundamental ones. There are more, but we can build all of these other logic gates from these three fundamental ones, right? So the logic gate is our AND gate. All right, similar to, again, in Boolean algebra, A and B, right, which sends an output, right? So here, in its most basic form here, right, output, right? So the output is going to be true or false. Now, all these have two states, right? Either it's true or it's false, okay? So the same thing for here is its output and its input, A, B. Okay, so its input being AB. All right. And then again, A and B means A and B have to be true, right? So if we have true, true, then that inputs true, all right? If one of them is false, again, similar to the truth table, right? So all these are guided by our Boolean algebra, our truth tables, right? It's just a physical manifestation of these, right? So the other logical gate is our OR gate. Now that one looks more like this, or again, it has one output, the output being true or false, and again, that is all depending on its inputs, right? Inputs go in here, all right? So this is our OR gate, okay? And again, in terms of the notation that we have seen, guided by that same notation, right? A or B. All right, this is A, this is B. All right, so OR means in this case to input something true, right? They both have to be, or excuse me, either one of them has to be true, right? Or both. All right, and then our third logical gate here, for the fundamental one, is the NOT gate. So that looks more like this. So that only receives one input, right? So this is our NOT gate. All right. Okay, so what this does is whatever the input is, so it gives the opposite output. All right, so the previous two, right, they're binary inputs, right, takes two, right, and gives one output. The NOT gate just is a switch that changes. If it starts true, it outputs false. If it starts false, it outputs true, right? So it takes in one input, right? Usually the input comes from another one of the other two logic gates, right? Either the AND gate or the OR gate, and it just changes the value of it, right? So if the OR gate gives you a true statement, right, then the output gives you, of the NOT gate gives you a false. All right. Okay, now there are other gates. Those are not the fundamental ones. There's something called a NOT AND. So it's really a combination of the AND and the NOT gate, a NOT OR, something called an exclusive OR. And what that means is that when exactly one of A or B is true, right? Normally when you say OR, either A is true, B is true, or both, right? The exclusive OR is only when one of them is true, does it yield something that it yields a true statement. All right, but again, all of these can be derived from our fundamental gates, right? So we'll stick to these three fundamental gates here. All right, and we can build these circuits from our propositional logic that we've covered previously in our Boolean algebra lecture from last week. All right, so the way we build a circuit, right, is by looking at really having knowledge of our Boolean algebra and starting from the outermost operator. Right. Okay. Excuse me. We start with the inner one, and our outermost becomes the outermost becomes the final gate. Right. How do I determine whether the whole statement is either true or false? Right. So here, let's take a look at here an example here. So here we have A and B, and not A or B. Okay. Now the outermost operator here is this one here, right? Because that's going to guide here whether the statement is true or false, right? It takes in this as its inputs, right? And those are compounded themselves, right? A or B, and then a not. A or B, A and B, you negate that. All right, so we want to set up a logic circuit. So looking at this, right, the last one is this AND one. So it's going to, here a rough sketch of this, going to output, all right, again, either true or false, right, or 1, 0, one being true, or one being false. And the inputs that are going to come in from here are the A and B, and here the not A or B. All right, and it's through the wires, right? But again, here these require their own logic gates to determine that, right? It's the same A and B. All right, so here I'm gonna switch over here so I can actually just show you what a circuit like this would look like, right? And I'll toggle between both of these pages here. Okay, so what we see here is we see the outermost right here, right? You see the AND gate here, right? And notice here it has a value of 0. It's off right now, right? So I like these. You can see the wires leading into all of our logic gates, right? And you can see which ones are, when they're green, that means they're true. They lead to something true, right? When they are red, it's leading to, right, something false, right? Again, all stem from our proposition A, B, right? And we have these compound propositions that we have here. So you see here the outermost one, that AND gate, which we see right here, right? That's the outermost one. And now you see feeding into this is the A or B. So first we need the logic gate out there, OR, right? So this is my OR gate, right? Here you see on the circuit elements, right? So we have all the different elements, gates, outputs, inputs, right? The inputs are propositions A and B here, right? So there's a bunch of other things. Again, this is most of the circuit stuff is out of my element here, but this basic ones that just kind of to model these Boolean propositions, right? We need this one that has the 1, our basic input, right? As you can see here down at the bottom right of the screen, once you hover over a particular tool, it'll give you just a brief description of what it is, right? So those are inputs. Outputs here, right, are just, I stick to just a general output, which you see at the end of my outermost operation here. All right, here it's at 0, so it is giving me a false reading. Okay, which makes sense, right? This last one here is a AND, so it has to feed into 2 green in order for that to be true. Okay. All right, and then we see here from there, we have our gates, right? Again, same shape, right? Standard shape, the AND gate, the OR gate, the NOT gate, and then these other ones here, the XOR, the and, the NAND, not and, not or, and the X not or. Okay, but again, just stick to that top row, top three. We can model everything in this class using those. All right, so now we can see here, right, feeding into that, again, the next one, you negate the and, right? Looking at this, negating the A and B, and then feeding into that the A or B. Okay, all right, and then from here we can play around with this and be like, all right, well, if I turn this on here, okay, now notice here I have A is on, so this gives me a true statement, and then B gives me a false statement, right? And now we can follow the circuit here, right? As it feeds into the OR gate, only one of them needs to be true, and here the A is true, so it feeds true into the outermost one, being the and then tracing back B as it feeds into the AND gate, right? Since only one of them is true, then it gives a false output, but the negation one, the not, flips it around to turn it on, right? And hence we have a output of true for the whole compound statement here. All right, and you can play around here. All right, you can just switch these, toggle them from on and on. All right, and you can see the different states that give you a true statement, right? Again, all this really is, we're visualizing our truth table here, right, in terms of these logic circuits. All right, so that's all they are, right? And again, a series, if you look at just going back to what these representing in our circuits, right, we could see how many of these, a series of, lots of these logic circuits here, right? But all of these stem from Boolean algebra, right? Which is why it's important to know how to calculate our Boolean algebra, right? If we're given a compound statement, how we can break it down, how can we generate this circuit, right? Based from just a propositional statement, right? Okay. So what we have here is, this is combinatorial logic. So there's no feedback loops, right? So every circuit computes exactly one compound proposition. Okay. So each one of these circuits, right, we have one compound proposition, and that outputs a true or false statement. There's nothing that, there's no feedback loops, right? Because those won't be able to describe propositions. Those are used for memory instead. All right. So common practice is just to label, right? Excuse me. Label with the appropriate operator, right? So here we would label like this would be the A and B, etc., just to keep track of all of our operations, right? Now notice here that the logic gates can take in one input, right? But our wire can split into more than one gate here. So we can split these propositions. They can go to more than one gate. Okay? And that's okay. All right? Okay. All right. So for the next video, we can build a circuit for any desired input-output table using only these three gate types. And yes, Boolean algebra lets us simplify the result, right? Which is why I think towards the end of the previous section, right, we asked, was there a simpler form of this compound statement? And that boils down to having just a simpler circuit, right, to represent the same operation.